Witam Was wszystkich na spotkaniu, na którym to Nakul opowie o mikroserwisach. Ja ze swojej strony chciałem zaprezentować firmę, którą reprezentuję, która ma przyjemność bycia sponsorem dzisiejszego spotkania. To firma nazywa się Software Plant i to jest taki, można powiedzieć, klasyczny startup. Parę słów o tym, czym się zajmujemy i kogo szukamy oczywiście. Zajmujemy się rozwiązaniami, które służą do project managementu. Brzmi nudnie, ale pod kątem technologicznym to jest to dosyć rozbudowane rozwiązanie, które angażuje w sobie dużo aspektów programistycznych. Bardzo ostatnio modnym u nas w firmie jest domain-driven design. Jednocześnie wykorzystujemy dosyć nowe technologie jak Angular 2 i co tam jeszcze jest, tak generalnie klasyka też oczywiście, jak tam Spring 4 i tak dalej. Rozwiązanie w tej chwili, pomimo tego, że startup tworzy grupa trochę więcej niż 10-osobowa, jest używane przez ponad 1200 firm na całym świecie, ponad 500 000 osób tego używa aktywnie, więc to jest już dosyć ciekawe rozwiązanie, bardzo mocno zmodularyzowane. O szczegółach mógłbym opowiadać dosyć długo, natomiast nie chcę, bo przyszliście tutaj posłuchać o mikroserwisach, więc chcę Wam tylko powiedzieć, że jeżeli jesteście zainteresowani pracą przy bardzo ciekawym projekcie, który angażuje też dużo energii tak naprawdę, jeśli chodzi o komunikację z klientem, jeśli chodzi o dyskusje jakieś technologiczne, jeśli chodzi o dobre podejście do tworzenia oprogramowania, o jakość tego oprogramowania, to zachęcam do zajrzenia na naszą stronę lub kontaktu bezpośredniego ze mną po spotkaniu, w trakcie spotkania. Nie wiem, czy coś jeszcze chciałbym dodać od siebie. Jakaś pomoc z sali? No, generalnie jest OK, tutaj pokazują mi koledzy, więc jeżeli ktoś z Was jest zainteresowany, to bardzo chętnie opowiem o szczegółach. A teraz chciałem już przekazać głos Nakulowi, natomiast wcześniej jeszcze chciałem przypomnieć, że na koniec spotkania będzie przeprowadzone losowanie jednej licencji IntelliJ'a, jedną mamy. To będzie na podstawie tych osób, które oczywiście zarejestrowały się na meetupie i jeszcze będzie do rozlosowania jedno szkolenie ze stacji IT, także to oczywiście też dla tych osób, tak? Na przyszłość generalnie, jako też może osoba, która jest zaangażowana we WJUG jako takiego, zachęcam Was do tego, żeby się rejestrować na meetupie. Osoby, które mają ochotę przyjść na kolejne spotkanie, bo na podstawie tego przeprowadzamy analizę tego, ile jedzenia zamówić, także pizza, którą dysponujemy na każdym spotkaniu odpowiada wprost liczbie osób, która się zarejestrowała, także zachęcam też do rejestracji, tak, na meetupie.
I would like to welcome you all on a talk about microservices. So a simple question. How many of you have heard about microservices? Okay, full room. And how many of you are doing microservices in like day-to-day life? Okay. So I hope after the end of this talk you will all have enough knowledge to write and develop your own simple microservices. So I would like to kick off this talk by discussing problems. Problems that are not only relevant to a big software giants, but problems that are also relevant to a medium-sized software house. And we will take a look on how monolithic and microservice architecture can handle those problems. Then we will take a look on few of the core concepts behind microservices, because remember, the goal of this presentation is that you can start writing and building your own microservices. And as we know, everything have its own pros and cons, so does the microservice architecture. And we will take a look on few of the plus and the minus. And last, the part which I like the most, coding. And I hope that the demos will work fine. But at the end, we will take a look on how to build and squeeze all the knowledge that we discuss in this talk into a feasible example, backed by Spring Cloud and Netflix OSS components. Here is a short info about me. I work as a consultant and an architect around JVM. Recently, I started writing my own blog. And if you are interested to find out some more presentations from me, just check out the slide here. A small remark, I'm not against monolithic, and I want to tell that it is possible to build beautiful monolithic applications. But usually the monolithic applications that we encounter in day-to-day life had a good vision, but the implementation and packaging was not so pretty. Hence we end up with something like this. It's not a golden rule of thumb that microservices should look like, monolithic should look something like this, but usually in day-to-day life we encounter something like this. So what are the common problems? First is complexity. Complexity can come in many forms. It can come in the form of new user stories, new requirements, competitive advantages. You can name them. But the complexity is not this nice guy which come to your door and say very politely, could you please let me in? Complexity just comes, slams your door in half, and if you try to hide yourself under pillow, it will find you. If you try to hide yourself under the bed, it is still going to find you. So the point I'm trying to make is that we as a developer have to face the complexity. We cannot avoid it. But in monolithic world, the complexity hits you directly on the face, which makes boarding of new developers or even moving existing programmers and increasing productivity quite difficult. For instance, a new developer have to go through a big README file, have to install a whole set of tools, libraries, database servers, God knows what node, then tweak those let's say to-do or README file to his or her own operating system. And at the end of the day, the task was very simple, just to add a new button in the GUI. But he have to set up all those things. Whereas in microservice world, the complexity is not disappearing. It is still there, but it is moved to a distributed layer. So hence, when we are developing microservices, we don't have to worry about hundreds of moving components all at once. With time, things becomes old and we need to upgrade our legacy components. Upgrading a monolithic components, first of all, is no fun, and second of all, because of technical limitations, it makes upgradation process quite a bit tough. Whereas in microservice world, when you want to upgrade, then as long as you are not going to break the SLA, which means service level agreement, and your APIs, you are free to refactor. Since monolithic applications require long-term commitment to tech stack, so it's quite hard to, for instance, rewrite a significant portion or part of the application just to upgrade the tech stack. So what the programmers do? We programmers are very good in making the workaround. So we start to create those missing features in our own tech stack. We try to adopt those features. Whereas in microservice world, we have the leisure to choose the appropriate tech stack for the appropriate problem. I'm not saying that each and every microservice should be written in a different programming language. But if, let's say, there is a library in another programming language that helps you to achieve your business requirement and business goals much more faster, then in microservice world, you have the flexibility to write that particular microservice in that tech stack. When we speak about monolithic, we speak about multiple responsibilities. One application that has multiple responsibilities baked into it. So when a new functionality pops up, it's hard to figure out which part of the application it belongs to. Whereas in microservice world, it's more extension of single responsibility principle. So when a new functionality pops up, we know where it belongs to, and we don't have to think day and night which package, which part should we put it in. And talking about standards, so in monolithic world, it's easy to maintain standards because we have one big application and practically all the team members are working on that. That's fine, that's true, but on the other hand side, the quality is hard to maintain. It's easy to mix bad and the ugly part. You are working on a code functionality, you went to holidays, someone have touched the code, and all of a sudden it's hard to keep up the hard and the good and the ugly part from combining together. Whereas when we speak about microservice, the quality is easy to maintain because we have small teams and large number of them, so each team is small in size. Hence they are quite focused on the quality. Because remember, in microservice world, the mantra is you build it, you ship it, you own it. Whereas when we speak about standards, since we have multiple teams, it's hard to agree on common standards. I'm not saying it's impossible, but it requires some, let's say, amount of enforcement to put. Refactoring the big world. Or usually we want to refactor, and when we start with a monolithic application, we start with something like this. But down the road, when we are refactoring, we end up something like this. Why? Because everything is so tightly connected that unfortunately we have to touch those parts of the application that we even didn't want it to touch at the first go. Whereas in microservice world, we are free to refactor. When we are refactoring a microservice, we even don't have to bother about hundreds of other parts that exist in the system. We can, if we are not going to break our APIs and service level agreement, we are free to refactor. We don't have to think about all those other components that somehow glue together, make my application as one, but during refactoring, I can just skip and forget about them. So enough problems. So now what are microservices? Well, it's a component-oriented approach to build applications, and each and every component talk to each other via language-agnostic API. The word micro here is quite nicely described, let's say, in computer world. I still remember back in my childhood days when I was attending a high school, I encountered the word micro, and my physics teacher told micro means 10 to the power minus 6. And I said, okay, what 10 to the power minus 9 means? He said nano, and I said 10 to the power minus 3, it means milli. The point is, when we change the unit, the word or the meaning of the word changes. But in computer world, micro means something small. And service, we all know to serve some purpose. So something small, but something small for me can be big for you, and vice versa. So the word micro in microservice, don't think about numbers of lines of code or numbers of methods. Okay, if you have to write like 10th line of code and your business requires you to do so, go home, party, eat pizza, and waste full night. But most of the time people try to kind of think that, okay, if I'm writing 20 lines of code, it is microservice. No, in microservice world, the micro word signifies the responsibility of each and every component. So each and every component should have one responsibility and as small responsibility as possible. So what are the core concepts when we are starting with microservices? First is service registry. Have any one of you heard about service registry? Okay, so just to break it down for all of us, let's imagine two applications, application A and application B. And application A want to communicate with application B. And let's assume the communication is a plain vanilla flavor. So we are not talking about any load balance or any proxy, nothing fancy here. So what application A want is to communicate with application B, and what it need, the minimal information that it need is the IP address of the service B and probably the port on which it is running. And then it can communicate pretty easy. But as soon as we step into the microservice world, these assumptions are shattered. Why? Because one of the key principles of microservice is scalability on demand, which means that you can scale each and every component as and when it is required. And in order to deliver such a promise, we usually end up in an infrastructure which provides no guarantee that next time when you will launch your application, it will be running on particular port or even on a particular IP address. You may ask that, okay, why we use such an infrastructure which provides no guarantee? So the answer is, for instance, cloud. You want to go, you don't want to spend money for the DevOps, or you just have too much work to do so. So let's say you move to a cloud, and a cloud provider provides no guarantee that next time when you will be running your application, it will choose the specific port. Usually it can assign some dynamic IP. So what we need is a single source of truth, a place where we can go and ask questions like, hey, do you know the address of service B? Or do you know on which port the service B is running? Or can you tell me how many instances of service B are up and running at this very moment? And this single source of truth is called service registry. There are many implementations of what I have discussed right now, but here are three of them. The popular ones, let's say. So if you are thinking about running your own private data center and stuff like zone-based partitioning and network-based partitioning is likely to happen, you can use Zookeeper. It is CP, consistency and partition. But if you are trying to deploy your microservice in an infrastructure where network-based partitioning and zone-based partitioning are the events that are going to happen at the regular basis, then the availability becomes more important than consistency. So then you can use Eureka, which is AP, which means it will be available and obviously partition. Console is another flavor. It provides really good set of features. I personally like it, and it's also AP. But for the sake of this talk, we are going to concentrate on Eureka. So Eureka is an open source service registry created by Netflix, hosted on GitHub. You can check out the source code and read. But basically, it consists of two parts, the server and the client. And in order to understand the server and the client, let me show you the communication between how a client and a server communicates with each other. So the first thing that a client should do is he should register, and he does so by sending an initial heartbeat, which is sent usually after 30 seconds when a client comes to life, which means we deploy an application. And once a client is registered, then he have to renew the heartbeat, which means he have to inform to a server constantly that I am alive, and he does so by sending a heartbeat after every 30 seconds. What happens when a client doesn't send a heartbeat and server doesn't receive any heartbeat from that particular client? Well, he waits for about 90 seconds, so like 3 heartbeats, and then he removes the client and he assumes that the client is dead. But let's assume that our client is registered and he is sending the heartbeat after every particular interval. Then the next thing he have to do is he have to fetch the registry. So basically, in fetching registry, he fetch all the information from the server about the possible services that are up and running at this very moment. And what he does, he retrieves this information and caches it. And as you know that every cache can become stale, so the client have to register, or let's say have to update this cache, and he does so by performing a registry update request after every 30 seconds. But an important thing here to note is that, sorry for this, an important thing that you should notice here that when the client asks for the update, he doesn't ask for each and every time information from the scratch. So he asks only for a delta information, which means the difference between a last fetch cycle and the current fetch cycle. So if you are deploying on a cloud, you don't have to think about that this communication is going to cost you a lot. And finally, when a client wants to shut down, he wants to go out from the space, he sends a cancellation request on shutdown, and a server just removes the instance from the registry. So the second concept now which we want to discuss is about load balancing. In microservice world, we can have 10 instances of particular service up and running. And let's say if I am a client and I want to communicate with service B, servers tell, okay, these are the 10 instances with which I can communicate. So which one I should use? Shall I pick the first one, the last one, or the middle one? Believe me or not, when we are doing big scale distributed system, such decisions can result in a smooth user experience or the worst user experience. And in order to target such a questions, we need a load balancer. And there are two options, a client side and a server side. And in a microservice world, the client side performs better. And Ribbon is the one which is built by Netflix and is provided as an open source component. It's a client side load balancer. It have lots of cool features, like for example, zone affinity. If you enable this feature, then the server is going to pick only, or the load balancer is only going to pick those services which are in the same zone. Hence, we can avoid cross zone trafficking, and even provide better user experience, and hence lower the cost even by avoiding cross zone communication. It also have a quite nice feature about resiliency, which means that dynamically it can find out if particular set of servers are alive or not. So let's say when I receive request from a server, and server said that 10 instances of service B were up and running, and during this 30-second phase, few of them got, let's say, shut down, or we have to kill the server. So the load balancer is clever enough that it is never going to redirect the traffic to those which are already dead. And lastly, it supports the rule-based load balancing. By default, it's round robin. But if you want, for instance, to implement your own load balancing using some weighted algorithm or keeping, I don't know, time of the day into consideration, you can just extend a class and override the particular methods. The third concept, which is quite important when we are building microservices, is an edge service. So I hope till now you are convinced that it is not a good idea to expose the info like address of a particular microservice directly to the client, because the address can change. But also remember, for instance, that in a microservice world or in a distributed world, let's say you have a scenario that you want to, for instance, from tomorrow start implementing authentication so that all the calls that are made to your APIs should be authenticated. Or you want to, for example, gather some monitoring data, like, I don't know, how much number of requests per every microservice is hit from, let's say, clients that are requesting from East Zone and West Zone. So in microservice world, such a things can be fulfilled using an edge service, which means that all the calls that are going to come to the microservice are going to pass through this gateway. And Zool is another open source component that is provided by Netflix. And it consists of 3 parts. It's pre-routing and a post. These are, like, you can call them stages, but these are the internal things which Zool have. And if anything goes wrong at any point of time, we fall back to an error stage. So let me demonstrate you how a request flows through a Zool. So a client make a HTTP request. So the first thing that comes into an action are the let's say, stage or triggers. What you can do in this stage, you can do stuff like authentication, for instance. But you can also do some custom logic, whatever you want, and there is no limitation of writing number of filters. There is no upper limit. You can write only 5 filters. You can write as many pre-filters as you want. But let's say you are done with processing the request at a pre-stage, then the request is forwarded to a routing stage. And in routing stage, you can, for example, implement stuff like dynamically routing, like find out where to route a request. And once you have successfully routed the request is handled by a post stage. And in this stage, for instance, you can do stuff like adding a default HTTP headers because you want to, let's say, collect the matrices, or you want to expose some data to a client which is standard, that after every request this part should be added to a HTTP header. And finally, the response is received by the client. So this is how the request flows through a Zool. An interesting question which you may ask is that the picture which I just right now you have seen, it's quite easy to implement in Java. You can write set of filters which will act and you are done. So why to choose Zool, or why to even go and incorporate a new component? Well, here are a couple of features which Zool provides and really excel. First is load shedding. So in a plain English, it means that we can allocate let's say maximum size for particular request, and if a number of requests goes above that limit, we can start dropping those requests, and Zool have those features built in. If you want to implement authentication and you have to pass the token to all the way and care about the security and OAuth stuff, it have baked in features for that. Sometimes you don't want even to redirect the response to a cluster. You just want to return as soon as the request hit the edge service, you just want to return some static response. And Zool also can handle this for you. This is the feature which I like the most. It is really like time saver, and it can save you few hours in production even to debug. So what you can do is, thanks to surgical debug filter, let's say you have a client who is trying to connect to your server, and only the client from the east zone and that particular client is receiving some sort of strange behavior during connection. What you can do, you can just use the surgical debug filter mechanism. You can write your own class, extending or implementing, I don't remember it's an interface or a class. And then what is going to happen is that all the requests that are coming from that particular client, you can able to redirect and perform some sort of analyzing. What more nice about this approach is you don't have to even recompile your code, because the code is written in Groovy. So these filters can be easily written in Groovy, and you can just write it and drop it on your production. So it's a real time saver, and can help you resolve those issues in which you have no possibility to replicate the production environment on a staging environment. And finally, stress testing. And what it does is, let's say number of teams worked on some feature and now all of them have pushed the code. The continuous delivery show that all our tests passed, unit tests are green, but still when we want to deploy on the production, we want to assess what is the build quality of such a new build or features which we are going to introduce. And thanks to stress testing, what we can do, we can configure Zool to slowly open and expose the traffic to this new build. So we can configure Zool to expose, let's say, 5% of the traffic initially, then 10%, then 20%, 30%, and we can every time monitor and write down like how the build is behaving over the span of time. And let's say after 75% of the time, we notice that the response time started to increase significantly. We can just say, okay, to the developers that till 75% the build was okay, but something you really have screwed up, and we can not continue by using the same build in the production. And the developers are happy because they have much more data where the things are going wrong, and the company is more happy because you have the possibility to not go like a Boolean approach 0 or 100. You can slowly and steadily increase the traffic. The fourth feature is failure management. Remember, in distributed world we have hundreds of moving parts, which means 101 things that can go wrong. And in order to kind of handle those things, we can write our own threads implementation, our own implementation of concept like semaphore, circuit breaker, so on and so forth. Or we can go and use Hystrix, which is another better tested open source component provided by Netflix. So basically, when you want to use Hystrix, when you don't want to go to your boss and say it's not my fault, and the third, the vendor, the API which I'm going to use, they are not responding. So in distributed world, you have no guarantee. You cannot assume that the component with which you are going to speak is going to respond, because each component is not this nice kid in the block. All of them are nasty kids in the block. They can talk to you or they can throw stones at you. So you have to kind of do precautions for your microservices. Which means, for example, a service is taking too long to reply because it have broken its SLA. What you should do, you should keep on waiting for that service to reply, or you should assume that the service is dead. Also, you need a fail-fast approach. So for instance, if you have thousands of requests coming, do you want to every time check if a service is dead, or you want to fail fast? And all those intelligence and nice logic is baked into a Hystrix. It's open source and is on GitHub. And the final concept that I want to speak about is distributed tracing. So before I will speak about distributed tracing, I want to mention an important aspect, which means speed. Back in 2008, I think, 2008 or 9 it was, Google performed an experiment. And in this experiment, what they did is they deliberately added some sort of delays in their search results. So for instance, it was 100 millisecond to 400 millisecond a search query was taking up. And what they noticed significantly is that the total number of searches dropped from 0.2 to 0.6%. So the people who were part of this experiment, they kind of started to use the search functionality kind of slower, lower and lower. And why I'm telling you all this thing about this experiment stuff? Because at the end of the day, if you have a technology, the consumer not only need a technology, he also need an experience. Which means, for instance, for a company like Google, even a difference of 0.5 to 0.6 or 0.8 can end up users who will use that service on a regular basis, on a day-to-day basis, or as per the report of this experiment, when the delays were introduced, in the first week the users were a bit patient, in the next week they were not so much patient, and during third and fourth week they started to kind of avoid using as many queries as they will like to make. So the end result is that you need a cool technology, but you also need to handle the user experience. And why it is important? Because when we go in a production, all hell break loose. We don't know if there is a problem, where is the problem, and how to debug it, especially in distributed world when you have hundreds of components. So what happened back in 2010, there were a bunch of guys who wrote a paper called Dapper, and it was a paper which take into consideration how to do distributed tracing, but at a level which is of a very, very large scale, and still it will be less and less and less intuitive. So they described that in today's, and it is back in 2010, so kind of 6 years old, they described that we have some nice rich internet application. And they say that those applications are composed of usually large-scale distributed system, which implies that those distributed system can be created using collection of software modules. And since they are collections of software modules, they can be developed by different teams and perhaps different programming languages. And what it implies all through is that when we have large number of services developed, potentially developed by large number of teams, or maybe small number of teams in various programming languages, they can span up to thousands of machines. So we can end up deploying those services not only on one machine, but on n numbers of machines. And the question that they want to answer by this research was that we want to understand the system behavior. So something that is complex, like large-scale distributed system and developed by different teams and different programming language, at the end of the day, they wanted to understand how the system behaves. So what they found out when they were writing this paper, they found out that the traditional approach doesn't work so well. So when we have a system that involves dozens of engineering teams and subsystems, then first of all, even if you have a top-notch developers who are like real ninjas who can do everything without even looking at Stack Overflow, even they can guess wrong about the root cause of end-to-end performances. And what it can result is when something goes wrong on the production, they can guess, they can make some guess, but since each and every team are working on a particular set of, let's say, functionality, it's hard for single person to keep all that info in his or her own mind. And then another approach was that, okay, we can introduce maybe a tracing infrastructure. And what it can mean is, for example, you are writing logs. Let's say I am entering in this method, I am leaving this method. Does it sound familiar? Is anyone have done like writing logs like this? Come on guys, do you do programming for a living? Okay, or maybe you are arrogant enough to not admit. Anyhow, when you write such type of log statements, it might end up resulting your production going out. So for instance, sometimes you can log so much info that the server is practically going down. So, and second problem with this approach is that it relies for active collaboration. So I can write pretty logs because I care about the standards, but maybe other guys, they don't want to care. So an infrastructure that relies for the active collaboration between n number of teams doesn't work so well. And these are all the findings of this paper. So what was the solution that they proposed? They proposed a solution which they implemented obviously inside the Google, but they were kind enough to publish this paper called Dapper. And you can read full paper, it's not so big. And then the Twitter, they implemented. So this is like an implementation, or it's based on Dapper. What it does, it is an open source distributed tracing system. And it does all those things and a lot more which I haven't mentioned here, incorporated in Zipkin, and it can scale to a really, really large scale. So these are the major, or let's say the important concept that one have to understand when we are doing about microservices. And now let's take a look on few of the pros and cons. So the pros are quite simpler. We are now in a component-oriented domain, so we are no longer thinking about a layered architecture. Also, we have this kind of leisure to use or choose appropriate tech stack, which means different programming language, different database storage units, so on and so forth. Scalability is something that comes for free. So we no longer have to worry about scalability. We can scale each and every component as per demand, because remember, we are in component-oriented approach, not on a layered architecture approach. And finally, the system is quite resilient in general. When one of the part get blown up, my full production can still work as a one single unit of the work. But however, all those nice features comes at some cost. So now we are first of all in a distributed world, which means in the past we had one application to worry about, and now we have hundreds of moving components to think about and somehow observe and build infrastructure to monitor them. And that brings me to the point 2, which means we need an arsenal of tools. So if you are doing microservices, you have to invest in building tools to monitor your tech stack. If you can't afford it, don't do it. Testing a monolithic application is quite easy. We have a one simple application, and writing tests for it is not as cumbersome when we are speaking about microservice. It requires different sets of skills. And finally, the transactions. So many times you have to battle by thinking about ACID transactions versus eventual consistency or mutual consistency. All right, so now is the demo time. I hope it will be working. So we are going to use Spring Cloud. And I'm not going to elaborate why Spring Cloud. You can use Spring Framework also, but it depends how much time and effort you want to spend in going to production. The demo is going to be quite simple. So what we have is a catalog service, and this service is going to let's say replicate a scenario in which one microservice needs to collaborate with n number of microservices. And these bunch of microservices on the right, they will show you, for instance, how we can write a simple microservice that don't have to collaborate with someone. In real world, whether it makes sense or not to have a microservice that don't collaborate, it depends on your business domain. Alrighty, so first let me show you a code. I'm in the, okay. So first thing which we need is the Eureka. So you remember the service registry, or you forgot? Come on, speak something. Google is not going to recognize you by voice. It's work in progress. Okay, so if you remember the service registry, you remember we had the client and the server part. So if you have to enable the server part, all you need to do is use this magic annotation @enable Eureka server. And what it's going to do is Spring is going to configure and fire up a Eureka server with some set of defaults. And you can override those defaults using application.yml. Once you have your Eureka server up and running, you want to now start registering some microservices. So for instance, let's take a look on price service. So as you can see, this is a microservice. So first thing, as you notice here, I have another annotation, which means @enable discovery client. And what this magic annotation does, what it does is it informs to the server that I am a client and I want to register with you, and all the registration process like sending heartbeat and everything is done. That's it. You can ask, okay, if it is so easy, what are the downfalls? Well, practically, if you have to overwrite something, just go to GitHub, find that particular property or read the Spring Cloud documentation. I hope the guys from Spring Cloud will work in writing more elaborate documentation. But pretty much that's it. You have two annotation, and now I can go and start coding my normal microservice. So for example, here is a price service. So let me show something here. Okay, so what price service does? Well, price service retrieves. It is a simple, I think all of you know how to build REST controller in Spring. So underneath, once I have the client and a server register, what I can do, I can write my REST controller. And here I am returning some product, some price. And in real world, you can fetch them, for instance, from some database, or you can use all sort of fancy stuff that you have to do. But we are back into the normal Java programming. There is nothing like hidden here. And just to show you that I have nothing hidden under my sleeves, and first of all, I have no sleeves, this is the price class. This immutable annotation is just for the groovy guys, but in general, what you can do is you can just write all that boilerplate code, or tell your IDE to vomit all those code and have here getter and setter. But I'm too lazy, so I just use that immutable annotation. And in the same way, I can build, for instance, a product service. So again, if I want to build a product service, I have to first register it. So I can go to product service. Again, I want to first thing do is register this, because it is a client for a Eureka. And once it's registered, I can go, for instance, to product service, which is another REST controller, and I can return some products. So as you can see, pretty easy. But now let's divert our attention to something which will be catalog service and a bit more interesting from our point of view. Product Eureka Turbine catalog. So as you notice that like all the other services, this service is no exception. It have to discover or register itself with the registry. But here you see another new annotation which is called Hystrix. And what this annotation in reality is doing, remember that this guy need to talk with other services, and those services can be up or can be down. There is no enforcement. So in order to handle those failures and incorporate the Hystrix support, all we need is annotate our class with @enable Hystrix. What Spring Cloud is going to do, it is going to again fire for us the Hystrix support with sensible defaults. And if you need to override them, just create a YML file and override the specific properties. When we are fetching the catalog, then this time the controller does some, let's say, two more things. So the part above is quite obvious for you. It's a REST controller, nothing fancy. But here, how we build a catalog? We say that we fetch the product, we fetch the comments, and we fetch the price. And then we build a catalog. But how does this fetching of products look like? So here, for instance, when I want to fetch the product, and remember, each and every of them are a microservice, so we can have n number of instances up and running. So in order to make a request, first I need a REST template. And since I need to inject the ribbon support, the client-side load balancer, the nice guy who take care of making the decision which one to talk to, all we need is to use the annotation @load_balanced. And that's it. Then what we can do, we can write our method. So for instance, here I'm doing something that you are used to do in day-to-day life, like use a REST template, call some URL, and map that result to a POJO, which is product in my case. And if something goes wrong, then I have annotated this method as hystrix command, because I don't trust product service. It can be up running or not. So I say, okay, execute this as a hystrix command. And if something goes wrong, then for instance, return some default value. It's not mandatory to return something default here. You can also return an error. But for the demo purpose, I just wanted to return something which shows the fallback mechanism. An important point when you are building microservices in real world is to avoid calling in the fallback a URL which belongs to another service. So for example, avoid calling external or avoid making external calls, because what if that call will fail? So then you are back to the original problem. And in the same way, I can fetch the products and I can fetch the comments. So for instance, here I will return some comments if the service is up and running. If it is not up and running, then I just return an empty array of empty list of comments. So one last question that you guys have probably is how these URLs are getting resolved, like price service and comment service, how all this URL resolving is going to work. So where is the last component which I spoke about, the Zool? So in order to build the Zool, what I need is I fire it as a Spring Boot application, and I just annotate it as @enable Zool proxy here. And when I'm done with this, what I can do now is I can go in my application.properties. Here I have for Docker, but let me go here. Yep. And what I can say, I can configure the roots here. So pretty easy. And if you even want to go a step further, you want to not avoid even configuring stuff in the property files, you can use another open source project from Netflix, which allow you to read property from some Git repo or something. And that's pretty much all from the coding point. So let's see whether it works. So I'm here on my terminal. Can you read it? No, probably, because now? Okay. So what I can do here is I can ask the service registry using a terminal to give me some information. Here, as you can see, it's a bunch of garbage, but if I try to parse it, for instance, here I'm using JQ library. So you can see now that this information show me, for example, on which port a particular microservice is up and running. I can go and verify the same truth using a browser. So this is the default GUI. I haven't wrote a single line to generate it, just annotation. And if you will upgrade even the version of Spring Cloud, you will have even more prettier page. But what you can do is you can go and to this URL. By default, Eureka runs on 8761. It is fully configurable. But if you go there, you have a nice page where you can see the status of your microservices. So I have catalog, comment, price, product, and Zool up and running. And what more I can do is I have somewhere down some more info like available memory, environment, CPUs, so on and so forth. It's not like full-blown monitoring stuff, but here it is a nice page where you can monitor and see the services that are registered. So back to the terminal. So let's say now I want to ask a catalog service to give me some specific catalog. So for instance, I want to fire a request to my local host because this is the current IP on which I'm running my infrastructure. And I issue a request and I get some response. So as promised via code, I get a catalog which has some ID, some product, some price, and some comments. These are the comments which are which I hope will be visible. Or wait, if I make it. Oh, that's cool. So this is nice. So here I have this information down here. I have author, I have content, and if I make it a bit smaller and see here. Okay, you see here, there are the comments. Here are the comments. And what I can do is, if I want, for instance, when I make a particular request here, you see I have here Hystrix which is monitoring the request. So for instance, what happens is, let's say I want to fire not maybe 1000, but let's say 100 requests to a catalog service. Then look what's going to happen. I made 100 requests, and since I enable the Hystrix, I can alphabetically sort them. So I have a comments, price, and product. Why these three of them only? Because remember, I annotated those three methods in catalog service with Hystrix command. So this is the dashboard. Again, it's prepared using Spring Cloud, few annotations. And here I can monitor when I make request. I can see right now that the circuit is closed and everything is nice. But now let's try to replicate something that can happen more likely in a real world. So for instance, let's go here and let's say I will kill my comment service. So what I did just right now is, previously I had 3 microservices which catalog service was communicating, and I killed one of them. And if you remember in the code, I have provided the fallback mechanism. So what is going to happen? Does my full application is going to blow right now or a part of it? Let's verify the truth. So first of all, I can go back here. I can ask Eureka service registry, what is the current status? And indeed, I have no comment service here. So you see, we have Zool, catalog, product, and price. I can check the same info here. So just to show you that it's not like something is cached, I just refresh the page and I don't have here a comment service. And now let's go here and let me make some sample request. And this time I get an empty array of comments. What is happening in Hystrix? Because this is something which is cool, and I want you to kind of draw attention here. Look, the status of the circuit is still closed. So which means if I make another request here and go back here, it's still asking the comment service, the circuit is closed. So why the hell I started using Hystrix? Well, till now it's true the circuit is closed, but let me fire again my 100 request, or maybe let's make it even 1000 request. And now you can start seeing all of a sudden that Hystrix able to detect that my comment service is down. So what's happening is, he checked that comment service is down, he made a request, and he noticed, okay, I didn't got a request within X number of seconds, and these seconds can be configured in property files. And when he noticed that n numbers of those requests happened, or let's say unsuccessful request happened, it opened the circuit. And opening circuit means that whenever a new request is coming, it is even not going to be bothered to ask the comment service that whether it's alive or not. What it is going to do, it will open the circuit, it will short circuit all the requests, and it will return immediately. That's why you can see I made 100, I'm still making a request here, and still it is short circuiting all of them. My application is still in one piece. Few things which are quite important. First of all, the threshold can be configured. For instance, you can control parameters like when the circuit breaker should open itself and how many requests it should take into consideration. But all in all, now you can see the benefit of using historics. When you have massive number of requests, you don't have to blow your full production environment. Okay, and one last thing I want to show. Does it works? Okay. Yeah. Good.
There was a fallback method, right?
Yes.
Is it a good idea in some cases maybe to have a fallback method of a fallback method? So to have another way of falling back.
Yeah, but the question that you should ask is like, if you cannot resolve a problem in first fallback, then how many fallbacks do you need to resolve the problem? You will not end up in n+1 steps.
Okay, maybe I have one. Okay, I must think of it. Okay.
Okay, if this will work, it will be nice. If it doesn't work, I will show you a screenshot. So meanwhile, I can show you something else here. A journal question I get when I'm giving talks at the conferences is people ask me that, do we have to use like all those infrastructure like Eureka and Hystrix and Zool just to get started? And the best part of the Spring is that everything is very, very kind of created in a very loose way. So you are not forced, for instance, to use Eureka and Hystrix together. In order to demonstrate such a thing, I have created here an application. It's hosted on Amazon, and what it does is I just ask free data available on internet from in US, and I just ask for some vendors which provide some sort of a food. So for instance, if I want to search for the chips, I write chips and I can adjust the distance here, and bam, I get some location here with this. So I can refresh it, probably, yes. And I can query the results. It's a normal application, Spring application. This deliberately I didn't made into a microservice because I want to highlight a simple point here. Here, for instance, I am in a project I'm working and I want to start using some knowledge which I gained from this presentation. And let's say I want to use Hystrix, for instance. No worries. What we can do is we can create a normal application like a Spring Boot application and just add in Gradle or Maven only that particular dependency, and this is a project which uses, and here is a, for instance, a Hystrix dashboard, and here you don't see red, and I hope you will not see. Here you see that we are firing, wait a minute, here I have to run something meanwhile. Okay, so we will have something. Back to here, and here what is happening is I have configured my scheduler in Spring to ask and poll this service, for instance, every 5 seconds. So after every 5 seconds, I'm polling a service which fetch the data from some API. But since this API service in no way had made a commitment to me that it will be up and running, so I just thought, okay, I can use Hystrix and I can annotate some specific class there and just build this code. If you are interested, I can push this code on GitHub, you can read it. But all in all, it's possible to build application using just only few parts from this tech stack. Okay, I have Zipkin. It doesn't look so bad, or maybe it looks so bad. Okay, anyways, I will try here. Let's go to the summary, and if I will have good luck, then I will show you. Okay, so I showed demo 2, incremental approach. Okay, so how the microservices looks in real world. Believe me or not, when you are going to a production, microservices are not only those 4 set of tools which you saw. You need, let's say, a development muscle to build those tools. Some of them are built, some of them you have to build. And you need all those tools, or not maybe all, some of them, to make a successful production environment. Also, when you are doing microservices, it's really important to have some sort of matrices that you can monitor in real time what's happening in your production environment. So this is a screenshot from an app. And here what we do is we have some sort of orders, and we wanted to monitor like when in last 15 minutes how the order processing looks like. Here we have GC pause, here we have thread states, DB connections, so on and so forth. And I think that's all from my side. If my demo is okay, so I cannot show you the Zipkin here today, sorry for this, but I think I do have somewhere screenshots. Okay, so believe me or not, if you successfully able to run Zipkin, which I have problem running in Docker at this very moment, then what you can do is you have a nice GUI which shows how the request flows through your entire system, and then you can even go and take a look on attributes like how many components were involved, how much time they took, so on and so forth. And I think that's it all from my side.